I'm Russell Ray with Power Engineering Magazine and your host for this hour. Today's event, Grid Stability and the Changing Landscape of Power Generation, will be presented by three specialists at ABB. But before we meet today's panel, I'd like to share a few housekeeping details with our audience. This presentation is both live and interactive, so you can ask questions at any time by clicking on the Ask a Question button in the presentation window. We will be saving those questions for the end of the presentation, but you can type your questions in at any time. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the home page at the Power Engineering website. Our panel today will feature Rodney Durbin, Director of the Clean Air Initiative at ABB North America, John Daniel, Senior Principal Consultant for ABB Power Systems Consulting, and Eric John, Director of Marketing and Sales for Flexible AC Transmission Systems at ABB North America. Our first speaker is Rodney Durbin, Director of ABB's Clean Air Initiative. Rodney has more than 20 years of experience in the power generation industry. Now it gives me great pleasure to introduce to you Rodney Durbin. Rodney, it's all yours.
Thanks, Russell, and thanks to Pinwell for hosting this extremely important event on a topic that has become very prominent for ABB in the last couple of years and also for our customers. I'd like to also give a special thanks to those who have taken the time to join us today for the webinar. So as we move through this, John and Eric will talk about assessing the impact of retirements and addressing grid stability issues that arise from those retirements of generating assets. However, before we get into the more technical aspects of the webinar, I wanted to spend just a few minutes talking about the bigger picture of the changing landscape. So I've viewed the industry through the lens of three primary macro factors over the last couple of years, the first of which being EPA regulations that have been increasingly stringent and driving decisions on the part of utilities to assess the fleet. Second is the abundance of natural gas that has been unlocked by the implementation of hydraulic fracturing. And the third is just the sheer age of the coal-fired generation fleet. So the work that I'm doing for ABB is really aimed at one thing, which is helping us to be prepared to anticipate rather than react to the shifts in the power generation industry today. When I started this journey a couple of years ago, I really viewed the world in very simple terms. And when we take the EPA regulations as the first domino in the chain, utilities have two basic choices that they're wrestling with. First of which is retrofit, where air quality control systems can be added to bring their fleets into compliance. The other choice to come to compliance would be through retirement of an existing asset. In some cases, that retirement can be absorbed by excess generating capacity on the grid. In other cases, that capacity will need to be replaced with primarily combined cycle gas generation, due in large part to the abundance of natural gas that's now available because of the hydraulic fracturing movement. Sort of the third category that we were looking at was grid stability, the piece that, frankly, I expected to be a much smaller part of this puzzle when we started this activity. However, as is often the case, things have changed. So if we look back to early 2012, the cross-state air pollution rule looked imminent. The mercury and air toxic standards limits were very strict and applied to individual generating units. And in fact, MISO was so concerned about supply chain shortages and outage constraints that they commissioned Brattle Group to conduct a study aimed at identifying bottlenecks. And in fact, in that landscape at that time, Brattle Group did confirm that some of those fears were well-founded. If we fast forward to today, the cross-state air pollution rule was vacated in August of 2012 by the D.C. Circuit Court. The mercury and air toxic standards requirements were relaxed to allow site averaging and consideration for capacity factor on individual units. So as an example of that, we saw companies like Southern Company go from 15 projected bag houses to 4. And then the introduction of the greenhouse gas regulations announced by President Obama in June of this year that are aimed at limiting CO2 from existing power plants, I think will further dampen the investment or the appetite for investment in existing coal facilities. So why then has grid stability become such an important part of the transition? In a couple of words, I think the answer to that question is excess capacity. If we look at the chart on slide 13, we can see a significant gap to the right of the vertical line in 2011 between power sector generating capacity and the consumption of electricity. In the situation, in the current environment where we are, the retirement of assets can in many cases be absorbed by excess capacity in the market. However, it has created a need for remediation in grid stability. So we find ourselves in a position where the industry needs solutions where my colleagues, John and Eric, have deep expertise. And for the rest of this webinar, we'll be sharing that expertise with the audience, Russell.
All right, great. Thank you, Rodney. That good information. Let's move on to our next speaker. Our next speaker is John Daniel. John joined ABB in 1998 and has been involved in a wide range of company projects. John also holds 3 U.S. patents for the design and control of power system equipment. John, it's all yours.
Thank you, Rodney, and good morning, everyone. Today, what we would like to discuss briefly are some of the issues that utilities will want to consider while they are considering the retirement of large plants. Coal-fired plants, other large plants such as nuclear have long served as the anchors for the interconnected transmission network. And in many cases, these baseload power plants define the characteristics of the local and regional power system. So it's important to understand what happens when power plants retire. Recently, a large utility in the U.S. was interested in retiring a large coal-fired power plant that was over 30 years old and provided some 500 megawatts of power. It also provided local voltage support and held up the local high voltage transmission grid. So it was very important for them to be able to study what would happen when it was retired. Well, there's a fairly large list of things that need to be considered when the plants retire because of changes to the network. And to briefly touch on some of those, for instance, there will be a generation load balance, of course, will be impacted. Unless you have a decreasing load level, generation will need to be replaced in some manner. The loss of the generation also potentially reduces the reserves that are available in the case of a contingency on the system, and those also will need to be made up somewhere. One important impact that can occur is the loss of the local system strength, the short circuit levels that are available. In essence, the system becomes weaker. And because of that, there are times that the installed equipment can actually become unstable. This has been seen in locations where the generation is remote and the power system is already weak and becomes particularly weak with the generation once it's retired. Instabilities may actually occur with other generations, such as wind turbines, if it becomes too low. When the plant is retired, it can be expected that the reactive power demand will increase. You need to bring the power in from longer distances as the higher currents on those transmission lines are pulled because the reactive power is not supplied locally, and so those higher currents also result in more reactive power consumption along the lines. Voltage stability and support is also impacted. The local voltage support is lost, and this can be related to, say, a tent with several tent poles with the generation holding up the voltage around, and when the generation is retired, a portion of the tent is not supported as well. This will increase the stresses on the other parts of the tent, but it won't necessarily cause it to collapse, although it could. So it's important to understand how the voltage support in the area is lost or weakened. The other impact here is that post-fault recovery of the system will become weakened because there's less of an ability to dynamically respond and to help stabilize the system. So with all of this, upfront planning becomes very essential, and it's important to carefully study the issues. These studies can include such things as power flow evaluations, voltage stability studies, dynamic stability studies, and even an evaluation of the transfer limits across the system. The benefit of the power flow studies is that it helps to identify the new power flow patterns and voltage profiles across the grid so that you can understand where support may be needed and how you might be able to provide that support. The voltage stability studies can give you an idea of how close you are to a system collapse. Many of you may be familiar with the figure here. It's a traditional nose curve, and one way to be able to address the loss of the reactive power is to place capacitors out on the system. But as you place the capacitors out on the system, you tend to extend your nose curve and come closer to a voltage stability limit that may make your system actually a little more sensitive to changes in the system voltage. These stability studies can help identify where the reactive deficiencies are and to identify the best locations for the steady state support. You also need to be concerned with the dynamic stability. There are a number of dynamic reactive devices that Eric John will be talking about here shortly that can be placed out there, and it's important to know where they should be, what kind of device might work well, the size of the device, and how fast you need it to respond to help keep the system up and operating well. And then finally, the transfer limit studies. The utility that I spoke of earlier, when they did the study, the conclusions of the studies indicated that the biggest impact associated with the retirement of their plant was not the loss of local voltage support, but it was a degradation in the regional transfer capability. So in other words, retiring their plant would adversely impact the amount of power that could be imported into the region that the plant was located. So these type of transfer limit studies, when they were performed, they indicated that it was necessary to be able to adjust this to beef up their network. In many cases, that's what the results will be. It may be that you can address this with new transmission, but of course, new transmission can be a very expensive proposition, both in terms of investment and in lead time. So the other possibility is to provide the local voltage support to replace the lost megavars, and that would help to improve the transfer capabilities in the system after the retirement of the plant. Of course, these types of replacements can come from things such as shunt capacitors, synchronous condensers, and SVCs. So the benefits of each of these are going to be discussed by Eric, so I will turn it back to Russell.
All right, very good. Thank you, John. Our next speaker is Eric John. Eric is the Director of Marketing and Sales for Flexible AC Transmission Systems at ABB North America. He rejoined ABB in August 2010 and has a wide range of industry experience. Eric, the stage is all yours.
Okay, thank you, Russell. So we'll jump right in and kind of summarize some of the key points that John Daniel just made about power generation and the consequences for real and reactive power. And the first one is fairly obvious, that generation provides both real power and dynamic reactive power in the form of VARs as contributions to the power system. And when generation is retired in load centers, reactive power needs of the system generally increase as imports increase. And there's an important point to be made here that VARs, or reactive power, are very highly dependent on their physical location in the system. And this is due to the nature of the impedance of the power system overall. The underlying physics of the power system mean that VARs are highly dependent on location. Another point is that dynamic reactive power is essential to voltage recovery following critical faults. And that voltage recovery has a high degree of sensitivity to the type of load served in a particular location. And loads in load centers, like a city center, is often dominated by small motor loads such as air conditioning. And those small motor loads drive the post-fault system dynamics. So kind of summarizing these points, we can jump in and talk about the solutions. And the focus of the solutions covered here today are those solutions that are dynamic in nature, meaning that they can change their output rapidly and that they have the capability to control their output on a continuous or a vernier basis. And the rationale for focusing on a dynamic solution is that a power plant, by its nature, is a dynamic source of reactive power. And so if a power plant goes away and reactive power is very location dependent, and you have loads physically close to where this retired power plant was located that need dynamic reactive support, it stands to reason that the types of studies the types of solutions that should be studied are also dynamic in nature. And so broadly speaking, the four options that we'll delve into include repowering at the same site, converting the existing generator, the machine, to a synchronous condenser. The third option is deploying a Greenfield synchronous condenser. And the fourth option is deploying a fax device in the form of a static VAR compensator or a STATCOM. And just to be fully complete here, we have a comparison of both static, meaning slow devices, and dynamic ones. And so the columns on the left, the capacitor bank and the reactors, are what we would refer to as a slow or a mechanically switched device. And we've included these for completeness because the question always comes up, well, we know that this generator provides reactive support to the system, we'll just install some capacitor banks. And the types of studies that John Daniel just mentioned show very readily that the dynamics are often the most critical aspect to the overall system reliability. And for our purposes of the webinar today, the dynamic devices have a higher capital cost than a static device. And so since they're so important in system reliability and they have a higher cost, we're focused on the more complex technology that's available to maintain grid stability. But this chart is included as a reference for completeness. So drilling down into option one, repowering at the same site, this seems fairly straightforward. If you have a power plant, you can reuse the existing transmission and possibly the transportation facilities and repower by building a new power plant. But there's some caveats to this, and the first is that the new plant must operate during critical system conditions. Most of the coal facilities that we're talking about today that are candidates for retirement are the low-cost producers, and therefore they're baseload units. That means they run 24/7 because they're low cost, and as a corollary to that, they're also available to be called upon to provide that dynamic reactive support following basically any system condition. They're always running because they're low cost, and therefore, regardless of what contingency comes up, they can be thought of as an anchor to the system. The new generation that gets sited on this location, it could very well be some kind of mid-merit combined cycle or a peaking unit, probably running on natural gas, based on the economics that Rodney had shown. And the unit might not be dispatched when it's needed for grid stability. And so this can set up a catch-22 situation, because the need for reactive support might not correlate to when the plant is operated, because often the time when reactive support is needed is during a time of peak imports. And by definition, your peaking unit or your mid-merit unit aren't necessarily going to be dispatched at a time of peak import, which could very well be when the system is most vulnerable from a reactive point of view, because again, the VARs are so highly dependent on the location. It's always possible to dispatch a generator for reliability purposes, but in a market environment, this shows up as a cost. It's often called RMR, or reliability must run. And this is deemed or can be deemed a market inefficiency, or it can be a cost to a vertically integrated utility that gets passed on. Most market environments are working to reduce RMR costs or other forms of market inefficiencies, and so it can be highly undesirable to be dispatching generation out of merit for reliability purposes. So if we go ahead to the next alternative, which is to convert the generator to a synchronous condenser, the conversion will provide rotating mass, which means that it contributes to fault current. And this can have some technical benefits to the system, especially in physical locations where the system is extremely weak. John mentioned that in some of his study work, he's found systems where when the generator goes away, you lose that sort of anchor tenant on the system, and you can run into stability issues. By converting the generator to the synchronous condenser, you can maintain some kind of contribution to fault current, and that can have a benefit in terms of the overall system stability. It can also be problematic if you're in a physical location where substation breakers are close to a limit as far as what their clearing capability is. And I'll come back to this point on the next one, but the spinning mass can either be a benefit or a drawback technically. The next thing to consider is the capital cost of the conversion. It's normally there is a cost, and it can be a fairly substantial, a 7 or an 8-figure cost to make the capital improvement, which can involve rewinding the generator, replacing the controls, upgrading the excitation system of the generator, and often the generator owner is captive to the OEM of the generator unit to perform that work. Related to this is the GSU of the existing generator step-up transformer should also be factored into the total conversion cost, because often if you convert the synchronous condenser, you're taking an old machine, something that's been operating for 30 or 40 years, and you're extending the life. If the generator step-up transformer is of the same vintage, and you're doing a conversion to a synchronous condenser, the synchronous condenser becomes a critical piece of grid reliability, and the generator step-up transformer is a single point of failure potentially in that overall system, because it sits between the generator and the transmission network that the synchronous condenser is there to support. So another factor to consider. The third are the operating costs of a synchronous condenser. The operating losses that would then be part of the transmission system for a synchronous condenser can be quite substantial. And of course, many utilities these days have initiatives to reduce their overall system losses. Similarly, you have ongoing costs in the form of, for operations. A generator that's been converted, especially if it has a hydrogen cooling system or a big lube oil system, is often a manned station. And so you have ongoing costs for the O&M folks who would operate the station. The last point to be made about the conversion is a commercial one, and that is in many ISO or RTO type environments, there's no straightforward mechanism to take a generator which sits in a unregulated pool of assets, if you will, and convert that to a transmission asset and earn a return under the tariff. And I know that there is talk within FERC and at the ISO and RTO level to compensate for reactive support, but there's not necessarily a contractual mechanism to be compensated for taking this former generation asset and converting it to a transmission one. The third alternative is to deploy a Greenfield synchronous condenser. And some similar considerations as you had for the conversion, although there are a couple of technical differences. One is that the new synchronous condenser requires its own step-up transformer if it's compensating a transmission system. And the transformer for that unit is going to be kind of a special animal. If you are running a transformer with very high VAR loads on it, the transformer can be driven into saturation if it's a conventional transformer. So the transformer needs to be specified properly to avoid, so that the secondary voltage is correct and that it's not driven into saturation when you load it with VARs. The second is that the Greenfield synchronous condenser is going to make a fault current contribution. And again, this can have benefits in the system from a system stability point of view, but it can also have an impact on station breakers. And this is a nuanced difference from the conversion, because in the case of the conversion, you already have a generator that would be contributing fault current. In the case of a Greenfield, you might be moving it to a different station, and you need to consider what the impact on the station breakers is of that incremental contribution of fault current. A Greenfield synchronous condenser, we've seen in the market that they have a higher capital cost, running 3 to 4 times the cost of an SVC. That's on a turnkey kind of basis. And this is based on our observations in the marketplace. Again, the losses and the financial impact of the losses should be evaluated. And again, introducing a fairly high loss device into the system can have consequences. And synchronous condensers have been around for a long time, 50 plus years, and I would say they're very much a tried and true kind of hardware for providing dynamic reactive support. The last alternative is the shunt fax device, a static VAR compensator, or a STATCOM. With an SVC or STATCOM, it is clearly substation transmission equipment. There are clear tariff mechanisms under FERC rules to earn a transmission ROI. You don't have a question about rotating apparatus and is it a generator or is it transmission. A fax device is capable of a response time that's much faster than a synchronous condenser or a generator for that matter. And there can be some technical benefits related to dynamic voltage recovery that you can realize with a faster response time. And this is especially true in networks where you have a high concentration of air conditioning load and shunt capacitors. A fax device will have significantly lower operating costs than the rotating options. Things like system losses are much lower, and a fax device is normally residing in an unmanned station. There is no contribution to fault current from an SVC or a STATCOM, and again, this can have technical benefits in the fact that it doesn't impact station breakers, but it can also the contribution to fault current can have benefits for synchronous condensers in certain cases for weak networks. SVCs have been used in transmission for more than 30 years, so perhaps not as much experience as a synchronous condenser, but with an SVC you have a device that's been well tried and tested in transmission networks. STATCOMs have a little less experience, almost 20 years experience for the first STATCOM installation, but again, not as much time as a synchronous condenser. And by way of example, these are the SVC and STATCOM installations that were deployed in the U.S. These are ABB project references, and this was our installed base coming up to 2005. And there are roughly 25 installations here. If we jump ahead to today, you can see that the number of units has more than doubled since 2005. And the units that are called out here are all related to the retirements of generation in a load center. And the SVC or the STATCOM that's called out in the circled pieces are basically grid reinforcements that are made for retirements of generation. And so to summarize the material for today, we'd say that the impact of coal plant retirements on grid stability cannot be ignored. There are key technologies available to resolve this grid instability when a coal plant is shut down, and it's really essential to do that early planning and analysis so that you can find an optimal solution, both from a technical point of view and also a cost point of view. So thank you.
All right, very good. Thank you, Eric. I want to thank all of our speakers for some very good, comprehensive information on perhaps the most important issue facing the industry today. It's time now for the question and answer portion of today's event. If you do have a question for our speakers, all you have to do is click on the Ask a Question button in the presentation window. You can type your questions there, and don't forget to hit that send button. Type your question, send it, and we'll have our speakers answer the question. And it looks like we have quite a few questions already, so let's go ahead and get started. Our first question is this. How does ABB see this playing out over the next few years with new GHG regulations being proposed, cheap natural gas and excess generating capacity being slowly absorbed by anemic economic growth? And I believe this question is directed to Rodney. Rodney?
Yeah, Russell, it's a great question, and I'll tell you, I occupy an awful lot of my day in trying to address that, and there are many factors, obviously, that influence it. But I think if we go back to slide 13, at least for me and for us, as long as we see that gap between the generating capacity available and then what is being consumed, which is what's represented by the gold line, which, according to this EIA chart, is being projected to go out to the 2020 time frame. I think that grid stability will, in fact, be a major piece of what we see in facilitating this transition, because it turns out that in this environment of excess capacity, VAR support and VAR remediation is a really cost-effective solution. So that's how I see that.
All right, very good, very good. Thanks, Rodney. Our next question is directed to Eric, and that question is, what are the most critical aspects to consider when trying to decide on SVC versus synchronous condensers? Eric?
Well, that's a great question, and I think the first one is really the stability-related issues. Do you need this rotating mass on the system to provide system stability? And we've actually seen some parts of the country where you have a pretty high level of penetration of distributed renewable resources like rooftop solar. And that is in this one part of the country on the West Coast, you have that coupled with power plant retirements along the coast. And the distributed generation has essentially no inertia, no rotating mass, and that can lead to a rather significant benefit of having fault current contribution in the form of a synchronous condenser. And so that's, I think, first and foremost, that in terms of a critical issue, that you're solving the fundamental needs of the system. But I think the second, once you've, all things being equal, you would then want to look at things like the operating costs, the losses, and the maintenance costs for each device. And by way of comparison, I've seen installations or synchronous condenser conversions. It's a case where a generator owner converted a rather large nuclear unit into a synchronous condenser, and because of the rationale being that, well, we have this existing asset, let's make the most of it. Well, that synchronous condenser was kept in service for about 10 years, but it was eventually replaced by an SVC. And the justification for that was the operating costs, the losses, and the maintenance for a lot of the auxiliary systems on that unit. So first and foremost is the grid stability and the need for fault current, and then the second would be the capital and the lifetime cost of one device versus another.
Okay, thank you, Eric. Don't go away, because this next question is directed to you as well, and the question is this. We've seen some utilities convert existing generators to function as synchronous condensers. Can you give us your thoughts on that approach? Eric?
Well, yes, and I think I think the rationale is often that we have that from the utility's point of view, that, well, we have an existing asset, let's make the most of it. I think from what I've seen, the capital cost to make the conversion can be as much as deploying a fax device. And I think what I've also seen is that some of these other things that should be considered, like addressing the lifetime of the generator step-up transformer. If you have the GSU transformer represents a single point of failure for the synchronous condenser. And again, if you're doing the conversion on the machine itself, and you're converting it for purposes of making it an insurance policy for the grid, it's a device that needs to operate under the most critical system faults to help voltage recover and maintain system security. To have a single point of failure in the form of a GSU transformer that's probably been loaded very heavily for 40 years or whatever, however long that generator was in service. I think that's a nuanced cost item that's often overlooked in terms of doing the conversion, and it's something that really shouldn't be.
All right, very good. Thank you, Eric. Let's move on to John. This next question is directed to John. The question is this: at what point should grid dynamics enter into the decision-making process when considering the long-term viability of a particular generating unit? John?
Well, I think that if you are going to be considering the retirement of a unit, it's important to consider the grid stability right away. The loss of the generating unit it not only potentially impacts the voltage and the dynamic stability, but you're losing a whole slew of benefits that the generation is providing to the system, and so it's important to study that early to be able to know what the overall impacts to the network are going to be. If it's a utility that owns both the generation and the transmission, that gives them a good sense of what kind of reinforcements might be needed within the system. If it's just a generation owner that is retiring the plant for some other reason, then that means that they're usually in an ISO or other type of regional authority, and that regional authority is going to want to know what the impacts are. So as soon as you are certain that there is a possibility of the retirement, I'd recommend running the study so that you can answer the questions that would surround it.
All right, very good. Thank you, John. We have a lot of questions that are coming in right now. We have well over 40 questions. I'm going to move down to 41, and if one of you could take this. The question is this: are there certain types of generators easier to be converted into synchronous condensers? Is this Eric? Can you answer that question?
Yeah, I'll try to take this one.
Okay.
It's kind of a broad question. I think the larger the unit that's being converted, the more complicated the conversion is going to be. So as a generator gets up in rating in terms of hundreds of megawatts, say, you have to contend with hydrogen cooling and more complicated lube oil systems. Depending on the age of the generator, you will most definitely have to make modifications to the excitation system and probably the controls on the generator. Now, the extent to which those modifications need to be made are going to depend on the age of those pieces of equipment and whether they've been upgraded or modified in the past. So in general, the larger the unit, the more extensive it's going to be to make modifications and operate. But again, each generator is almost a special animal, and it's something that needs to be evaluated really by the generator OEM to decide to what extent the modifications need to be made. The other aspect is how much capability in terms of reactive support do you need. The generator is specified, or a generator is delivered with the so-called D curve, which defines what its real and reactive capabilities are, and on a continuous or on a short-term basis. And so it could be depending on what the needs of the system are when that generator goes away. It could be possible to modify that curve and increase the amount of reactive capability if the machine is only operating as a reactive device by either rewinding the machine or changing the cooling, making modifications to the cooling system of the machine, either the rotor or the stator or both. And so there are a lot of questions that really need to be investigated, I would say with the help of the generator OEM, to assess what's required to do. But I don't think there's a really hard and fast answer to what's the easiest one to, or what's involved for a particular kind of generator.
Okay, very good. Thank you, Eric. Let's move on to the next question. We'll move on to let's see here. Yeah, we'll move on to number 37. Are there special factors related to the increasing retirement of large nuclear power plants and the prospect of others going the same way in the near term? Would anyone like to take that?
Yeah, this is Rodney. I'll try that one. I think special factors may not be exactly accurate. The closure of the generator is not that dissimilar from what's happening in power, but we have seen what appears to be a rash of closing of nuclear plants with San Onofre and Vermont Yankee in progress, Crystal River. Not sure if we expect that to be a trend that continues, but certainly is adding to the importance of these grid stability projects as we make the transition to a new generation mix.
All right, very good. Thank you, Rodney. This next question may be for Eric. Number 44. Can the reliability of fax devices be quantified in terms like mean time between failures? Does that make sense?
It does, and I don't normally think in terms of MTBF, but for our purposes here, there are availability and reliability guarantees that are regularly made with fax devices, and in fact there are guidelines within IEEE for reliability and availability figures in terms of the definitions and so on. A typical commercial guarantees are written, I would say, with just about every SVC or STATCOM project that are on the order of 99% annual availability and 2 or fewer forced outages per year. And then you can show statistically in terms of failure rates on the underlying components and subsystems and how those build up to using MTBF figures for individual components, how those build up to an annual availability figure. So I'm not sure if that answers the question, but I think it speaks to perhaps the essence of what the person's getting at.
Yeah, I think so. I think so. Thank you, Eric. We'll move on to the next question. This is for John. How much time is required to conduct a thorough study?
Well, that's a good question. It's very system specific. There are a lot of issues that need to be considered with that. Depending on the nature of the network and where it's located. However, a ballpark figure you should, for planning purposes, is probably 3 months or so to be able to thoroughly investigate all of the issues that may be involved, from voltage stability to the transient dynamics, and what changes you may need to make to the system to mitigate any system difficulties that would arise with the retirement.
Very good. Very good. I'll move on to question number 35 here. And if one of you could take that. Is there a significant loss of inertia when replacing coal with combustion turbines, combined cycles, wind, and solar?
This, John, I'll go ahead and try with that one. Obviously, when you retire a plant and the machine changes, you're going to have a change of inertia. If when you talk about replacing it, you replace it with multiple machines where the total inertia is greater, then it might not be a loss. It may actually be an increase in the inertias that are there. And of course, the performance of the system will change with that. One of the nice things about replacing with combined cycle and the gas turbines is that they do have a significant inertia. So even if you don't fully replace the inertia that was lost with a big machine, you haven't lost all of the inertia. With wind turbines, the plants, as it builds out, the manufacturers these days are able to give something of an inertial response out of the wind turbines, provided that it's okay with everybody to operate in the way that they need to be able to provide that. In essence, they have to spill some of the wind, not produce quite as much to be able to allow for an inertial response if it's necessary. If the replacement of the generation is from things like the solar panels, where it's really distributed around, well, they will not provide any kind of an inertia for them. They don't have a mass or the capability of being able to do that in quite the same way. And so replacing the generation with solar, you'll be able to provide some level of reactive power support. Certainly you'll be able to provide a replacement of some of the real power generation, but you will have a loss in the inertia by using that.
All right, very good. Thank you, John. Our next question, I think, is directed, this may be a question for Eric. The question is, what is the life expectancy of an SVC?
Another really good question. The life expectancy is at least 30 years, and SVC is made up of conventional transmission and distribution, or transmission gear, power transformer, capacitors, air core reactors, and this is equipment that routinely has a life of more than 30 years. The SVC also uses power electronic valves, cooling system, and controls, and the controls are most likely the element that needs to be replaced after 10 to 15 years. And I think this is something we're seeing across the industry. If you have a digital computer-based control system, the life expectancy is going to be less than for that. The life expectancy for that particular subsystem is going to be less than the other hardware. So for the overall station, 30 years, and for the control system itself, that can be upgraded or replaced after a period of about 10 to 15.
All right, very good. Thank you, Eric. I think I'll move on to 42. The question is, how does the reliability of SVC and STATCOMs compare to other PF and grid stability solutions? Anyone willing to take that on?
This is 42?
42, yes.
I mean, the SVCs and STATCOMs are designed to be as reliable as any other piece of equipment on the grid. You don't want it. You certainly would not want it to be less reliable from an availability reliability point of view, because you're designing the system for an N-1 contingency, and you don't want that contingency to constantly be being the loss of that fax device. And so that's why you see commercial guarantees written around 99% availability, which is consistent with other types of equipment, whether it be a generation plant or other T&D gear that's used on the grid.
All right, very good. Thank you, Eric. I think I'll move up here to number 13. The question from our viewer is this: do you have a maximum fuel mix to be optimized for grid stability? Anyone like to take that one on?
This is Rodney. I'll take it. I think it's difficult, and one of the things that I should mention is most of our comments today are predicated on North American market, and so we all see this shift toward natural gas because the supply is such that future price projections for natural gas are so low. But in terms of, unless I'm misinterpreting the question, I don't know that anyone can say where we have a max fuel mix to optimize for the stability of the grid. And I think this, as an industry, is one of the questions that we're all trying to answer. What will the future grid sort of look like, and what will be more important tomorrow than it is today?
I see. All right, very good. I think we have time for one more question, and we'll end it with this. It's kind of a broad, general question. It's number 17. And the question from our user is this: what's the impact of distributed generation on the issue of grid stability? Anyone would like to answer that?
Well, again, it's one of those issues that it depends on what part of it that you're talking about, that you're considering. Most of the distributed generation that folks talk about are the solar panels being distributed around different houses or businesses, things like that. Again, the power that's there and is great for supplying the load and helping in that way. Other devices in conjunction with the solar panels are typically necessary to help provide the reactive support, because you want most of that energy that is there to be sent out into the system rather than circulated. So the design isn't specific to provide reactive support there. And of course, such things like that don't contribute much to the fault current levels, the short circuit levels, or the inertia of the system. On the other hand, there are smaller DGs that have been talked about over the years that might provide very small levels of inertia, but nothing along the lines of what you might see from a central plant.
Very good, very good. I think we'll go ahead and end it there. I want to thank all of our panelists for a very informative discussion. I have learned a lot, and I hope you have too. I'd like to let people know we greatly appreciate your feedback and input, and as you exit today's webcast, you'll be asked to take a survey. And again, we would greatly appreciate any input that you could offer. Well, you've been tuned in to Grid Stability and the Changing Landscape of Power Generation, brought to you by ABB. On behalf of Power Engineering Magazine, I would like to thank today's speakers for their time and willingness to share their expertise. This presentation will be archived within 24 hours and can be accessed from the home page at www.power-eng.com. A reminder email message for the archive will be sent to registrants, complete with a direct link to the archive. We thank you for joining us today, and we look forward to seeing you again at future webcasts. Take care, everyone.